this is to help you with the assignment called Rates of Reactions for the inside. Now, hopefully you have watched video 2 from the notes, and you've seen what a rate law looks like and all that kind of stuff. I picked to do 8 with you, number 8 from the packet, because it involves the most work. The other, number 7, number 9, and number 10 only have 2 reactants each, so those are less work, but it's the same type of work. So I picked number 8 just so that I'm doing the one with the most work for you, or with you, because you should be following along, not just looking for the answer at the end, okay? So we need to write the rate law for the following reaction using the data given. Now, it should be an indicator, but we don't use the products at all. So if it helps you, just cross off the products, okay? The products are not included in the rate law. The rate law is dependent upon the reactants only, okay? So the rate law is going to be, and you need to put rate equals. If you don't, you're going to get points taken off. Rate equals the constant K times each of the reactant raised to a power, raised to an exponent. So we've got the concentration of the reactant. So BrO3 negative raised to a power, I'm just going to throw in X, times the Br negative raised to Y, times H plus raised to Z. Okay, now you're not going to get the points for this. You would get 1 out of 3 points for this problem by just writing that out. But I want you to actually solve for what are X, Y, and Z's exponents. What are those exponents? So that's what we have to use the table and that information in the table to get there. Okay, so we're first going to focus on solving for X. So now, when solving for the exponent on a reactant, you need to make sure that that reactant's concentrations change when you pick the 2 experiments, but the other reactants involved stay constant, okay? So for X, we are going to use experiments 1 and 2. And that is because if you look at 1 and 2, so this is for X, it's the same value for the concentration for both columns. So looking vertically, sorry, I did that wrong when I first highlighted, but so the Br is held constant. It's the same number in both experiment 1 and experiment 2. Same thing for the H plus. They're the same, they're held constant. So when they're held constant, that means we can forget about them because something divided by itself is just 1. Okay, so for X, oops, sorry, I need to change back. For X, we'll compare experiment 2 to experiment 1. Now, I like to plug these in so that I put the bigger numbers in the numerator and the smaller numbers in the denominator so that it's easier for me to figure out the math. So if it's rate equals K times, I always put the rates first. So on the left side I have the rates, and I'm going to do 2 over 1. So this is just for you to see I'm doing experiment 2 divided by experiment 1. So we have 1.6 times 10 to the negative third is the rate for experiment 2 over 8.0 times 10 to the negative 4 is the rate for experiment 1. Now the rates are equal to the concentrations raised to X, the power of X. So experiment 2 goes on top, and that's 0.20 raised to the X power over 0.10 raised to the X power. They're both raised to the same power. Okay, so we can simplify this by, we can go ahead and divide, and when you divide the left side, the 1.6 times 10 to the negative third divided by the 8 times 10 to the negative fourth, that is equal to 2 for the left side. Now the right side, we can also reduce that. So if they're raised both to the same power, then we can simplify it by saying 0.2 over 0.1 all raised to the x power. Well, 0.2 divided by 0.1 is just 2. So now we have 2 is equal to 2 to the x power. Now, if we need to figure out what x is, 2 raised to x gives it itself. So whenever you raise anything to the power of 1, it's its own self. It's its own number. So that means that x is equal to 1. So that is the first exponent that we solved for. We have to do all of this again for y and z. Okay? Now, just save that for later, but let's move on to y. Okay, well for y, I don't know if I can change my highlighter color. Let's see. Let's try blue. Okay, so for y, we need to not hold BR constant, but we need to hold the BrO3 and the H plus constant. Okay, so looking here, in order to find y, I'm going to take, since the BR is y, okay, I'm going to compare 3 and 2, 2 and 3. So for y, I'm going to compare 2 and 3. And the reason why I chose that is because it's constant for the H plus in both of those, and it's constant in the BrO3 for both of those. Okay, so remember, the one that you're looking at has to change, but the other two columns that you're not focusing on have to stay the same. Okay, and then we're going to use the rates for those as well. Okay, so now I got to flip forward because I don't have space and I don't want to erase anything. But, so this is 4y, so you can see what we're doing here. 4y, I'm going to take, remember, bigger divided by smaller, just works for me. So 3 is bigger, so I'm going to take 3 on top and 2 on bottom. So rates come first. Rates are not raised to the power, but we have 3.2 times 10 to the negative 3 over 1.6 times 10 to the negative 3. Those are the rates. They're not raised to the power of y because they are the rates. Only the concentrations get raised to the power of y. So then on the other side, I'm going to go ahead and simplify to just being 0.2 divided by 0.1. So I skipped a step where I raised both the concentrations to y and then simplified it. I'm just jumping right in here because I know mathematically that's what's going to happen. Okay? Well, let's simplify each side. Simplifying each side, the left side equals 2, the right side equals 2 to the y power. So that means that y is also going to be 1. Just so happens that they are the same. Okay, so save that for later. That is our second exponent, but we still need to solve for our third one. So the blue highlighter is for the y, the yellow highlighters for the x. X was that guy. So now let's go with, oh, I don't know, purple, sure. Purple is going to be z. Okay, well, so with z, again, the z column needs to stay, or it needs to change, and x and y need to hold constant. So looking here, the only ones that x and y, or the BrO3 and the BR, are constant are 1 and 4. So it's going to be 1 and 4 that we compare. And that's because it's constant in 1 and 4 there, and it's constant in 1 and 4 there. They're both 0.10s in both columns. So you can hold constant things that are not next to each other. The experiments don't have to be in order or next to each other in order for you to hold them constant. It's just whatever you can figure out. Okay, so this is for, oops. This is for z, to figure out what z is. And just looking at the data, experiment 4 data is larger. So I'm going to take 4 on top and 1 data on bottom. So for the rates, remember rates are on the left, 3.2 times 10 to the negative 3 divided by 8.0 times 10 to the negative 4 equals, and I'm going to again jump right into how I know that they're going to be raised to the same power. So I'm just going to plug it to the power of z right now. the concentrations are 0.2, 0.20 over 0.10. We've had that a lot, this problem, and that's okay. So now simplifying, the left side of the equation, dividing those out, equals 4, equals, and then the right side, 2 to the z power. Well, here we go. It's not going to be a 1 this time, right? Because 4 is what you get when you raise 2 to the z power. So 2 to what power equals 4? 2 times 2. So z is equal to 2. Okay. Now, this is not the answer either. You can't just circle what the exponents equal. You need to write them back in rate law form in order to get full points. Okay? So what that looks like, I think I need to get everything. I need to get another slide. Here we go. So with this new slide, here we go. I got it. Our rates. So it's everything that we had before. Rate is equal to k. But now, instead of plugging in x, y, z, like we saw, and I had highlighted them before, you know, x, y, and z, we are now going to plug in the numbers we solved for x, y, and z. So we still have the concentration of BrO3 negative, but that's raised to the first power. So now, if you want to put a 1, you can, but if you don't put a 1, I know that you are implying it's a 1. Okay, so I'm not going to do that. Times the concentration of the bromide ion, the Br negative. That Y was also a 1, so I'm just going to leave that there. Nothing to put in. And times H plus raised to the second power because we solved for 2 for Z. Okay, so this right here is your answer for number 8. Okay, when I say what is the rate law, write out the rate law. You need to figure out what those exponents are using the data given to solve for that. Okay, sometimes they're all going to be 1s. Sometimes they're never going to be a 1. You just have to figure that out. Now for number 6, you are not given any data, so you can't really solve for what the exponents would be for number 6. So for number 6, that is the case where only putting x, y, z, whatever exponents you want for those spots is okay for number 6. I hope you're listening and not just watching the video without audio so you can hear that. So number 6 only, again, you can write out the generic rate law, which the generic rate law is plugging in x, y, z, whatever exponent letters you want to without actually solving for them because you can't. Okay. And then on number 10, number 10, you know that you have 2 reactants. You have NO and you have O2. So that means even though you don't have an equation, you will have those 2 reactants that you need to use to figure out what the rate law is. Okay? I will talk to you when I get back, and I hope this helps.